As the universe matured, galaxies began to organize into vast structures. Threads of matter stretched across incomprehensible distances, forming what scientists now call the cosmic web. This immense network of filaments, voids, and clusters reveals a grand architecture shaped by gravity over billions of years, a skeleton upon which the visible universe is built. But how did this colossal structure emerge from the randomness of quantum fluctuations? The answer lies in gravity's relentless pull, a patient force that over cosmic time transformed minute imbalances into galaxies, clusters, and superclusters. Picture the early universe as a vast ocean of mostly uniform density, but with tiny ripples, overdense regions, seeded by those initial quantum perturbations. These overdensities had just enough mass to attract more matter. Over time, as the universe cooled and expanded, those regions grew denser. They became the birthplaces of stars and galaxies. As matter clumped together under gravity, it also dragged surrounding matter toward it, creating elongated filaments that connected clusters like tendrils in a spider's web. What emerged was not a random scatter of galaxies, but a finely patterned tapestry. This structure, visible in large-scale surveys like the Sloan Digital Sky Survey, resembles a three-dimensional web stretching hundreds of millions of light-years across. And yet, this cosmic web is far from uniform. The vast voids between filaments, some stretching for hundreds of millions of light-years, are almost completely empty. These voids are among the most mysterious regions in the universe. They represent areas where matter is so sparse that galaxies are rare and time seems to flow differently. Some cosmologists even speculate that these voids might one day offer portals to test the fundamental laws of physics away from the noisy complexity of matter-rich space. At the intersections of filaments lie galaxy clusters, the densest regions of the cosmic web. These clusters can contain thousands of galaxies bound together by gravity and swimming in hot gas. They are the largest gravitationally bound structures in the universe and act as cosmic laboratories, helping scientists understand everything from dark matter to galaxy evolution. But the cosmic web doesn't just define structure, it influences motion. Galaxies aren't simply drifting aimlessly through space. Their movements are guided by the gravitational contours of the web. We now understand that our own Milky Way is not isolated, but part of a vast supercluster called Laniakea, meaning immeasurable heaven in Hawaiian. This supercluster spans over 500 million light-years and includes more than 100,000 galaxies. Laniakea itself is just one branch of an even larger structure, the dipole repeller and great attractor, regions of space that either repel or draw galaxies in vast cosmic flows. Incredibly, our galaxy is currently moving at about 600 kilometers per second through space, pulled by the gravitational influence of distant clusters. To map this structure, astronomers use techniques like redshift surveys, where the light from galaxies is measured to determine how fast they're moving away from us. Combined with gravitational lensing, the bending of light by massive objects, scientists can reconstruct a 3D map of the universe's layout and better understand the invisible forces at play. As we study this map, we also begin to ask deeper questions. Why this structure? Why these laws? Why does matter arrange itself in filaments and not in some other way? These patterns might be dictated by the fundamental constants of the universe. Values like the gravitational constant, the speed of light, and the mass of particles. Even small changes in these constants could result in a very different cosmos, perhaps one incapable of forming stars or galaxies at all. The structure of the universe, it seems, is not only shaped by physical laws, it also shapes the possibility of life, consciousness, and complexity. This has led some physicists to explore the idea of a fine-tuned universe, the notion that the conditions of our cosmos are precisely set to allow for intelligent life. While controversial, this idea invites profound contemplation. Are we simply lucky inhabitants of a universe with the right rules? Or is there a deeper reason why the cosmos appears designed for observation? Adding another layer of intrigue, the cosmic web may even affect how galaxies evolve. Galaxies within dense filaments tend to grow faster, collide more often, and experience higher rates of star formation. Meanwhile, those isolated in voids evolve slowly, more peacefully, with less dramatic encounters. In this way, a galaxy's environment can determine its destiny. Modern simulations, like the Illustris and Millennium projects, recreate these cosmic structures in powerful supercomputers, modeling billions of particles of dark matter and gas over cosmic time. These simulations confirm what we see in telescopes, but they also hint at structures beyond our view, suggesting the universe may be far larger and more complex than we can currently observe. Ultimately, the cosmic web is more than just a map of galaxies. It is a living record of the universe's history, a fossilized imprint of gravity at work, sculpting the cosmos over 13.8 billion years. And within this grand design, we find ourselves not at the center, but as part of the pattern, a single strand in the web of infinity.